Welcome to the Epic Flight Academy Commercial Pilot Course. Remember our 3 keys to success and please hit that subscribe button. Today, our topic is energy management. Now, to help us understand and make sense of this topic, our resource will be the Airplane Flying Handbook 8083 3C. That's 3 Charlie. Chapter 4. Now, just a couple of clarifications to get started. In the Airplane Flying Handbook, Chapter 4, on page 4-1, about halfway down, we see that the FAA tells us that a flying airplane is an open energy system. What is that? Well, there are 3 energy systems: open, closed, and insulated. Now, for everyone who was awake and paying attention in high school or college physics, take a quick break. And for the rest of us, an open energy system exchanges both matter and heat energy with the surrounding environment. Look at this pot with no lid boiling on the stove. The water going in and the steam boiling off is matter being exchanged with the atmosphere. And the heat going back and forth between the pot and the stove, when it is either heating or cooling, is heat energy being exchanged with the stove. A closed system exchanges only heat energy with the surrounding environment. So look at this pot with a lid boiling on the stove. The water, once inside the pot, is not going anywhere. It may boil into steam, but it does not escape. This system is closed. However, heat is still going back and forth between the pot and the stove. And finally, an insulated system where neither matter or heat energy is exchanged with the surrounding environment. Look at this thermos full of hot water. The hot water inside the thermos is not going anywhere. No water getting in, no steam getting out. And because it's insulated, no heat is moving back and forth between the thermos and the atmosphere. It is an insulated system. Now, back to page 4-1. So, why does the FAA describe your aircraft as an open system in flight and not closed or insulated? Well, take a look at your aircraft. It takes on avgas and burns it. It is exchanging matter with its surrounding environment. And as the aircraft uses fuel to provide power, it stirs and heats the air, releasing energy in the aircraft's wake. It is exchanging heat with its surrounding environment. Learning to visualize your aircraft as an energy management system is important for every pilot. So, to that end, I'd like you to start thinking with me in terms of an energy-centric approach to our aircraft in flight. So to begin, our 172S, it's not a helicopter, it's not a glider, it's not a balloon. Our 172S is a fixed-wing aircraft that burns fuel. So we have 3 sources of energy at our disposal. Number 1, chemical energy. That's the fuel in our tanks. Number 2, kinetic energy. That's the energy in our movement, our airspeed. And number 3, potential energy. That's the energy in our altitude due to our mass and gravity. Now, visualizing it this way is key because this is how we control the aircraft in flight. We control power, airspeed, and altitude. Balancing these three as a pilot is the process of energy management. And as pilots, we have two energy managers literally at our fingertips. Number one, the throttle, which manages our total energy. And number two, the elevator, which is an energy exchanger, also called an energy converter. Now, we say that the throttle manages total energy because it can provide to us both kinetic, airspeed, and potential energy, altitude, by using chemical energy, that is, by burning fuel. We say that the elevator exchanges or converts energy because by pulling the yoke aft and raising the elevator, we can give up airspeed to gain altitude. Or by pushing the yoke forward and lowering the elevator, we can gain airspeed by giving up altitude. The elevator exchanges or converts energy between kinetic and potential. It cannot add or subtract total energy. Now, with these basics in place, let's jump to our first graph here from Chapter 4. Notice in the upper right where it says lines of constant total specific energy or energy height. Now, important note here, your energy height in these graphs is not your altitude. Your altitude, your potential energy, is shown along the left-hand side of the graph. Your airspeed, your kinetic energy, is shown along the bottom of the graph. Now, on this graph, as we move from point A to point B, along the same energy height line, what is being depicted is that the total energy of the aircraft is the same. Kinetic energy of 100 knots plus potential energy of 6,000 feet at point A is the same total energy of 6,500 as kinetic energy of 250 knots and potential energy of 4,000 feet at point B. What else should be understood here is that 6,500 feet, the total energy line, would be the maximum altitude the pilot could achieve in a zoom climb. A zoom climb is done by using your energy exchanger, the elevator, to trade airspeed and altitude. The most altitude you could zoom to at 100 knots would be 6,500 feet, starting from 6,000. You can also see on the graph the most altitude you could zoom to at 250 knots would still be 6,500 feet, starting from 4,000. Pretty cool, am I right? Now you're viewing your aircraft from an energy-centric approach. Now that we understand how to read this energy map, we can see two things. Number one, as we move along the same energy height line by using our energy converter, the elevator. The elevator converts airspeed and altitude, but the total energy remains the same. And number two, if we want to move across energy height lines, we need to use our total power controller, the throttle. In this second graph, we can see that we can move along an energy height line of 5,000 from A to B and also from B to A by use of the elevator. However, to jump across energy height lines and, say, make a jump from A to C or D or E, we need a total power increase. The same is true for a descent. On our graph here, to move from C to A, if we just push the nose over with the elevator, we'll come down in altitude, sure, but we'll move along the same total energy line and increase kinetic energy, our airspeed, and maintain the same total energy. So, our descent from C to A on our graph here from 11,000 to 5,000 will require a decrease in total energy. In other words, a total energy power reduction by, anyone?
Bueller.
If you said reducing the throttle, you are exactly correct. So, with our understanding of energy states, the energy map, and three types of energy, number one, chemical, our fuel, number two, kinetic, our airspeed, number three, potential, our altitude. Let's wrap this up with three basic energy management rules. Now, these three rules we find in the Airplane Flying Handbook 8083 3C, as in Charlie, Chapter 4, page 4-10. For each basic rule, we will look at total energy, throttle, and converting energy, elevator. Shown here, rule number one. If you want to move to a new energy state that demands more total energy, then total energy, throttle, increase the throttle setting so that thrust is greater than drag, thus increasing total energy. Energy converter, elevator, adjust pitch attitude as appropriate to distribute the total energy being gained over altitude and airspeed. To climb at a constant airspeed, pitch up just enough to maintain the desired speed. To accelerate at a constant altitude, gradually pitch down just enough to maintain your path. Upon reaching the new desired energy state, adjust pitch attitude and throttle setting as needed to maintain the new profile. And shown here, rule number 2, if you want to move to a new energy state that demands less total energy, then total energy, throttle, reduce throttle setting so that thrust is less than drag, thus decreasing total energy. Energy converter, elevator, Adjust pitch attitude as appropriate to distribute the total energy being lost over altitude and airspeed. To descend at a constant speed, pitch down just enough to maintain desired speed. To slow down at a constant altitude, gradually pitch up just enough to maintain your path. Upon reaching the new desired energy state, adjust pitch attitude and throttle setting as needed to maintain the new path speed profile. And shown here, rule number 3. If you want to move to a new energy state that demands no change in total energy, then total energy, throttle. Do not change the throttle initially, but adjust to match drag at the end of the maneuver as needed to maintain total energy constant. Energy converter, elevator. Adjust pitch attitude to exchange energy between altitude and airspeed. To trade speed for altitude, pitch up. To trade altitude for speed, pitch down. Upon reaching your new desired energy state, adjust pitch attitude and throttle setting as needed to maintain the new path speed profile. Well, folks, this wraps up our review of energy management. Now, there is still a lot to learn about this topic. But now that you have the basics in place, you're off to a good start. So join us next time.